A warm welcome to another episode, Data with Nick the Greek. Um, Today's topic gonna be a follow-up to our previous topics, partitioning and coalesce. So today we're gonna look on another way how you can repartition your data. So basically, actually you guessed it already, the command is called repartitioning. But we're also gonna use the time again to just have a short overview and recap of why we're doing partitioning and why it's really important. And then we really gonna deep dive a little bit today into how repartitioning is working. And then as a follow-up in the next session, we're gonna really use a little bit deeper repartitioning and coalescing to show some scenarios where it really helps to improve the performance, similar to what we already started with coalescing in the previous episode. So with that said, we're gonna start our Spark session, have our data generator set up again, and just to have a look into the data just once again to understand, because we do some group by later on to analyze the data a little bit. So here what we can see is the ID generated by Spark, and what we did here is we just made a string out of it and then took the first character out of it. And if you, for instance, now generating data up to 20,000, you guess it, the first character of the number gonna be mostly 1. So meaning if you would group by or cluster our data based on the first number within the ID, it's gonna be quite skewed, for instance, for 20,000 IDs. And that's what we're gonna observe in a little bit when we do the partitioning. We also have two functions today, which we're gonna use for analysis. So the first one I finally encapsulate into a function to not do it manually. So what it does is just clusters the data based on the data frame. Clusters the data based on the partition ID. So just to run an example so that you can understand how the function is looking like. So we have our generated data frame here, SDFgen, the number of rows which we said were 20 in this case, and so what rows per partition. Okay, of course I have to run the function first. So and what we can see here is it just shows us how the data is partitioned. What we can do as well is with the second function, we can also do the same thing, just group by a specific column. You guessed it right, it's gonna be the ID first column, just to show how it looks here in this case. So basically we can see, okay, now in partition 0, we have 0, 1, 2, 3, 4. Then the next partition has those values. And then we can see, okay, ID first, 1 is in partition 2 and 3 in the most times. So basically that's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. But more in a bit about the data. So now let's do a recap about partitioning. And I found here also an interesting Stack Overflow link, but let's just sum up why partitioning is really important. So the first thing is what we already saw, we need a very good parallelization. And it means two things. So first of all, you don't want to have unused cores, meaning one core is doing all the job and the other ones are just standing there, meaning you have resource which you basically don't use. And the second thing is that, well, you're using all your resources somehow, but one core, for instance, is doing much more work than the others. This is like when you have like skewed data. And that means, like we already saw it when we selected our number of cores, we always took the factor or a value dividable by the number of cores, which you can also check here with the Spark context default parallelism, which gives you the value, which is basically the number of available cores. And there are recommendations of a factor 2 to 4. But of course, it depends. If you have a very small data set, you rather just go with the number of cores you have to really distribute the data, because it means also you have overhead as more partitions you have for the distribution and scheduling. Of course, if you have now a really big data set and you're not able to increase the number of cores with more workers or a bigger machine, of course, as you're gonna reach your out of memory limitation or memory limitations, you might rather want to even go ahead and increase the factor even higher. But important here is definitely you should go with a partition number, which is a factor of your default parallelism, your number of cores. The second topic is about data skew. So if you have skewed data and one partition has significantly more data than the other one, it can happen. So there are scenarios also if you have a lot of small partitions and a bigger partition where it somehow can get equally, but the best way is to get rid of skewed partition sizes. So best to have a uniform or maybe a worst case a normal distribution of your data. By those two things, as you saw it in the previous session already, you get the best performance and the best parallelism using Spark. As Spark, based on its nature, it's parallelizing based on the Spark memory partitions, which at the end become tasks in the stage. And the stage of the job. Then in regards of a partition size, so what you want to avoid is to have a too small partition, because you just don't use the available memory in all. So it would lead to more smaller partitions, and that is going to be overhead. On the other hand, you don't want to have really big partitions. So usually I checked online, there are some rules, not more than 1 gigabyte. There are some recommendations between 100 and 1000 megabyte. Of course, it depends on your memory, but usually with a very high memory size, you're definitely gonna have out of memory issues, because always you have some variations of your available memory, or it depends what you're doing additionally, setting up classes, initiating classes, etc. This can also like fill up your memory and garbage collection, and this kind of might lead to errors, meaning you can increase the stability by not using too much out of your memory. Also, one example is the max partition bytes, which we're going to learn when we're going to load files in one of the next episodes out of storage, is 128 megabytes. And yeah, it really depends on the machine. If you have a machine with a lot of memory, of course, you could go higher. But the recommendation to stay around this size is actually a good one. It's something you just have to try out a little bit. Yeah. Then regarding the distribution overhead, so saying just one more time, we did some tests with 2000 or 20,000 partitions. You already saw that like the scheduler and the distribution had some overheads and time loss in there, and so we see that a slightly higher number of partitions with not too big partitions definitely has a benefit, but making them too small also is not good. So if your green part, the execution time of one of your tasks is well less than 90% or even significantly less, like 10% is your execution time, and the other part is like just scheduling, something is wrong there. And one reason could be that you have this distribution overhead with just too many small partitions. I found a rule also online. I also added a link here to check it out. That below 100 milliseconds is just too short if a if a task is running within this time. So you should really think about increasing the partition in this case. So let's jump to repartitioning. So, and how it really works. So let's just open the documentation shortly and see how the function looks like. So the function data frame.repartition takes two parameters. One thing is the number of partitions, as before, also coalesce. But here we have also another benefit. We can also take one or multiple columns to partition. And here you see some examples. So you can set a number, you can set a number of partitions and a column. We're gonna see it before. You can also just specify the column based on which you want to partition. And important, you can also set like multiple columns as the value takes multiple columns in as input. Going back to our notes. What's important compared to coalesce, we now can either increase or decrease the number of partitions, and repartitioning requires a shuffling compared to coalesce. So you saw it was a narrow transformation, no shuffling, just one stage. Even though I learned that also coalesce sometimes the circumstances where there might be some shuffling, but usually it isn't. But repartition does have a shuffling. A benefit, on the other hand, is you remember, like if you're doing coalesce, it just unions multiple partitions together, which can lead to skew in the data. But repartition really works with a round robin fashion. It just divides all the data in a uniform partitions. So the size of partitions you're gonna see in a bit when we see some examples is really equally. And instead of partitioning based on the number, you can also partition based. Okay, we have to correct it based on a column, and if no number of partitions defined, so basically if you partition only based on the column, it goes with the shovel partitions parameter. We're gonna learn it later when we have wide transformations that it's relevant, but this value defaults to 200. So let's start with one sample data set. We're gonna do here our counting, do our analysis. So we have 2000 rows. You see we have a uniform distribution as you created our file, but you can also see that we don't have a uniform distribution also if you check on the ID first column, which I mentioned before. And let's run our baseline job, which we're gonna evaluate in a bit. So let's have a look on the number of partitions. We start with 4. So what we're doing now is we repartition the data frame down to 3. Okay, so you can see we have now 3 partitions, and also what's important, if you run our aggregation, we can see that each of the partition really has the equivalent number of rows, not as it was with coalescing. So let's do and try to increase the number of partitions. Also this works. We have also equal number of partitions, and in this case 8% of the data divided by 12 has been distributed. Now let's do the same thing just based on a column. So I defined here, just for rerunning purposes, the 200 with the default parameter for Spark shuffle partitions, and you can see the number of partitions is 100. And if you're running here our aggregation, we can now see, okay, some partitions are missing. So where are all my partitions? And this means, and that's something it's really important to know, is repartitioning can generate empty partitions. And you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are filled with data. Also quite skewed, as we saw already that the number the number of our first ID first is a little bit skewed. So that's also like something we should be aware of if you're using repartitioning, especially for narrow transformations. You usually, except of writing, you might not want to repartition by column. So let's do also the same thing based on the columns. So basically, what you can see is that in each partition, in this case, we have only one ID first value. So partition 3 got all the 7s, partition 18 got all the 3s, and so on. But still we have the 200, and what you can see here is we actually have only 10 values. So you might think, okay, let's partition based on a lower number here. So let's set our shuffle partitions to 20 and do the same thing, and the result looks pretty similar to before. So we have the same distribution, just other partition ID this time. Now, as you saw, we have only 10 values, so let's finally do it with 10. And yeah, we have here something really interesting. So you would have thought that, okay, we have 10 different ID first. Repartition moves them into different partitions, but that's something I fully haven't understood by myself and surprised me when I looked in it. So only 6 of the 10 available partitions have been assigned with data. I mean, I could imagine that it has something to do with the round robin, but round robin usually means, okay, it just goes through all the data in a round robin fashion, just assigns one data point. After okay, here I have to correct me, round robin is of course not the case if you define a column. It's actually hash partitioning, sorry for that, but we're gonna see it in a bit when we are looking into the Spark UI. Yeah, but still I'm surprised about the results, that for instance 2 is not assigned to another partition but stays in this partition. So I thought maybe let's go even lower with a number, and also here it does something really surprising. So instead of moving the partitions, so first of all, one partition is still not assigned any data to, and instead of assigning data to a partition which has less data, it just fills up the partition which already has 55% of the data up. So you can see it down here. Partition 4 has 55% of the data, and then those additional data are still added there. So that's something we should just be careful of, to know that they're gonna be empty partitions and some skew when partitioning based on the column. So now let's run 3 jobs, once with our data frame where we partition from 4 down to 3, one from 4 to 12, and one where we repartitioned based on the ID first column and increased our partitions from 4 to 5, and see how this really looks into this in the Spark UI. So we're jumping over to the Spark UI. Let's refresh and see if our jobs are there. And the first thing we're gonna be looking on is 4 to 3. So what we can see here first is we have 2 stages. So we have our exchange operation here and the second exchange operation here. And what happens initially is we have our 4 tasks, as you would expect, And then we have the shuffle write operation, which is writing the data to disk so that it be gonna be loaded by the other cores as Spark usually does with shuffling, which we're gonna deep dive also in a later stage. So I jumped away. So let's jump to the second stage. No, that's not the second one. That's the second one. So now we have, as expected, the three partitions and equivalently the three tasks, which is just reloading and processing and noob writing the data afterwards. And so we can also see that we have here an equal distribution as we saw before with 6,667 rows. So looking now also for the first job, let's also have a look into the SQL data. So you can see that we have the shuffle records of 20,000, and what's also important is in the details that you see here the data is repartitioned to 3 partitions using a round robin partitioning method. So now let's have a look into the second job. So you can see similarly the same thing happens. Also, if you're gonna see here, we see, okay, we have 4 tasks which are running. This shuffle write time takes a little bit longer. This might be due to the higher number of files we might have to write. To be honest, I'm not 100% sure why one of those tasks takes so much time. And at the end, as we target 12 partitions, we're gonna see, okay, we have a nicely distributed partition, but what we can also see doing the writing, we see that we have a high distribution of execution time here, even though data is uniformly, and this might happen here due to the scheduler overhead in this case. And of course, we have some deserialization time, which happens when you're reloading the data back from the storage. So now the interesting part gonna be actually the third one. So here we are doing something slightly different. We are increasing to 5 partitions, but we also partition by the by one of the columns, so ID first. So here we can see again our 4 tasks being saved. And then in the second stage, we see the 5 ones which are being loaded. And here, for instance, that's something we also observe and can see here again. We have some quite distribution here. So first of all, you can see the one task which is empty. So we saw before in the distribution, one task doesn't have any data, so you can see it here. And then we can also see that some tasks, or the one task which had like 75% of all the data suddenly, which leads here to some quite skewed pipeline execution. So you can see that one task really takes most of the time, and it determines at the end the stage execution time in total with 38 milliseconds. And the last thing what we're gonna do is also as a comparison to look in the Spark UI, and here we can see it's not a round robin anymore. It's now hash partitioning by the ID first column, and that's like the main difference if you partition only by the by number of partitions, or if you're partitioning additionally by a column. And hash partitioning means we have a hash key, and then there happens some sorting in the background of this key to reassociate the data to the new partitions. There's something similar which gonna happen later on also into Y transformation. So we're gonna deep dive. So to finish up and wrap up the partitioning topic, I added here also some reference, but just as a sneak peek, what we're also going to look in the next session, but also in later sessions, where you want to use repartitioning. So the one thing we already observed is if you come with a number of partitions which is not divisible by the number of your cores. We said already we want to adjust the partition. So if you decrease it, you might go with core less or repartition. If you want to increase it, for instance, you have 7 partitions, you would want to go up to 8. You only can use repartitioning. Then if you have data skew, we saw that coalescing doesn't help usually much, or at least only in some scenarios there you would like to use repartitioning to really handle this. Then that's something we're gonna see in later episodes. So join operations can benefit of repartitioning, because what the join operation usually does, it's sorting the data. So it does a sort merge as a default. It's sorting the data, which is hash based on the key. And if you already have repartitions your data based on a specific key you want to join on both tables, it sometimes or can be more efficient and reduces just a shuffling and sorting operation in the background. Any other operations, so a join, but also like an order by, can benefit of a repartitioning. So, but that's always like a checking like what's the effort of the repartition, which is shuffle operation, it needs time, compared to the benefit of having a fast execution of, for instance, an order by on any other shuffle operation. Bigger filter operations, as we already saw it with repartition, but also bigger filter operations can lead to empty partitions. So if you have 10 million of rows with 1,000 partitions, and then you apply a filter which only leaves 10 rows at the end, and then you suddenly have 1,000 partitions where with 10 rows definitely at least 990 gonna be empty, and then you have some additional operations afterwards. You have to know that some of your partitions gonna be just empty and might create some overhead when writing, when doing some other white transformations or whatever afterwards additionally. And that's something we should be dealing with coalescing or repartitioning. And you can, of course, influence your writes. So that's something we're going to learn very soon. As well as that, in short, the number of partitions influence how data and how efficient data are going to be written, similar to a noob write where we already analyzed the performance, and a high number of your writes can make the saving unoptimal. So here I wrote optimal, but that's something I should correct. And the file creations, so for instance with Parquet, depends on the number of partitions. So you're gonna see if you have 5 partitions in the background, you have 5 snappy files. If you have 1, it's gonna be only 1 file. And with that, that's it for today. I think this was already enough input. The only thing what I want to say is we are really deep diving a little bit here. And in a lot of scenarios, the effort of really getting out all of the max performance, and really optimizing each line of code with the perfect number of partitions and so on, is of course effort. So generally you would focus on there where you really see performance issues, where like, I don't know, 10,000 of rows suddenly take 5 hours to execute, as a bad example now, or really a low number of data suddenly takes a long time, really where you have the feeling it's not working as efficient as it should. The other thing is I would say sometimes nice to have, but it's still important to understand what's happening in the background. And if you're now developing a new pipeline, to have a quick check if your number of partitions is exploding, you can already avoid it in advance, even if it might not make a big issue for a small number of rows. I saw it in a use case recently. Suddenly data exploded by a lot, and suddenly we had performance issues in the background. And that's something you, of course, want to um, but it's always a balance of effort and performance outcome as well. And with this, thanks a lot for listening today. As always, if you like the sessions, feel free to subscribe and also to comment if I explained something wrong. If you have questions, I'm also learning by those sessions by myself. And with that, goodbye and see you in the next session.